Okay, let's see the solution of test number 28. This question is a little bit long. The question is, a conducting bar with mass m of 0.2 kg slide on a frictionless rail that lie on an incline having an angle theta equal to 25 degrees with the horizontal ground. There is a uniform magnetic field B equal to 0.5 Tesla point down in the region of the incline. The rail have length of L equal to 1.2 meter. At the end of the rail are connected by a resistor R equal to 1 ohm as shown in the figure. If the bar slide a constant speed V, your bar slide with a constant speed V. Okay. Find the value of the speed. Okay. This maybe a little typo here or missing. Slide with a constant. With a constant. Where this should be the width. Which means the width or the distance between these two rails. Okay. Anyway, the variable show itself because you can see L is L here. So you can see the meaning of each variable by the context of the problem or by looking at the figure. Okay. Now, how can we calculate this? We want to find the speed V, and we know that V is a constant. So it means that the net force on this bar must be 0, right? Now, what is the force acting on this bar? Of course, there is a gravity acting on this bar, and this gravity tries to pull this bar to slide down the incline. So it means that there must be another force that cancels the gravity, and we know that this is a magnetic force. This is because when the bar moves, and in this region there is a magnetic field. So it means that when the bar moves, the magnetic flux in this loop increase. And from Faraday law and Lenz's law, there must be the electromotive force in this loop. And this electromotive force drives the induced current, and this current will produce the induced magnetic field that against the external magnetic field. And also, when we have the current in the external magnetic field, there is a magnetic force on this bar, and this magnetic force or the component of this magnetic force will cancel the effect of the gravity. Okay, that is the whole picture of this problem, and the value of V must be the one that create the induced current, and this induced current create the magnetic force that cancel the gravity. Now, let's go to the detail of the calculation. First, we know that the flux in this loop change. So, we must first calculate the flux of the external magnetic field that pass through this loop. Okay. If the distance of the bar from the upper end of this bar of the rail is x, and the distance between these two bars is L. So the area of this loop is XL, right? And we know that we have a plane here, the plane surface here, and we have a uniform magnetic field. Okay, so it means that the flux is equal to the product of the projection of the magnetic field on this surface or on this plane. Okay, and we can see that the angle between B and the vector A is this angle, right? This angle, okay, which is pi minus theta. So we may say that the flux is equal to BA cos pi minus theta, but cos pi minus theta is equal to minus cos theta, and since A is equal to x times L, so we have this equal to the minus B XL cos theta. Okay. Now, the change of the magnetic field dV by the T is equal to the change of this term, but we know that B is a constant because the magnetic field is uniform, L is a constant, theta is a constant. What change is x? So when we do the derivative here, we will have the dx by dt, which dx by dt is equal to v, right? So when we do the differentiate here, we get the velocity v here. And from the Faraday law and Lenz's law, we know that this derivative must equal to the minus of the EMF, right? So we have this relation. Now, by cancel the negative sign, we must have that the EMF is equal to the BLV cos theta. And the current that passes through the circuit is equal to E over R, which is the Ohm's law, right? So we have the current is BLV cos theta R. Now we know that there is a current in the region with the magnetic field, so we must have the magnetic force. And the magnetic force is, the magnitude of the magnetic force is equal to ILB. We can say that the magnetic force is ILB because we know that the direction of I and B is perpendicular. Okay, this is the direction of B, and I must pass through the bar like this. So you can see that I and B are perpendicular to each other. So when we calculate the magnetic force, FB is equal to IL cos B, but L perpendicular to B. So the magnitude of the magnetic force is ILB sine pi over 2, and sine pi over 2 is equal to 1. So we have that FB is ILB. Okay. Now, this is very important that we have to know the direction of I. Okay. We can see that the direction of I, if we look at this figure, will point into the plane, or if we go back to this figure, this is the direction of I, the induced current. We know this because we know that when the bar moves, the flux in this region increase. So the induced current must create the induced magnetic field that against the change or the increase of the magnetic flux from the external field. Okay, so this must be the direction of the induced magnetic field, and follow from the right hand rule. If your thumb point in this direction of I, and when you curl your forefinger, this is the direction of your forefinger. So we know that the induced current must flow in this direction, or if we look at this figure, this is the direction of the induced current. Now we can use the right hand rule again to find the direction of the magnetic force. Now you if you point your forefinger in the direction of induced current, point your forefinger into the plane, and the magnetic field point out of your palm. Okay, your thumb will show the direction of FB, which point in this direction. So we have the FB point in this direction, right? You can see that if we dissolve the component of FB along the surface of the incline and perpendicular to the surface of the incline, we have these two components, and you can see that the angle here is theta. So this component is FB cos theta, and this component is FB sin theta. This FB sin theta will cancel with the normal force. Okay. And this FB cos theta, that is cancelled with the effect of the gravity. Okay. If we look at this figure, this is the bar, and we know that there is a gravitational force acting on the bar in this direction, right, which is mg. And when you see the component of the mg parallel to the surface of the incline and perpendicular to the surface of the incline, we have these two components, mg sin theta here and mg cos theta here. Okay, we know that this angle is theta because if you look at this angle plus this angle must equal to pi over 2, and this angle plus this angle must equal to pi over 2 too. So we know that these two angles are equal. So we have that this component is mg sin this component is mg cos theta, and this component is mg sin theta. This component together with this component of the magnetic force will be cancelled with the normal force, and this component mg sin theta will cancel with fb cos theta to make the bar move with a constant speed. Okay, so at this point we can write this expression that fb cos theta, this component, is equal to mg sin theta, this component, and we know that fb is equal to this term, so we can substitute this term here to get bl square cos theta square v over r is equal to mg sin theta, and by rearrange this equation we get v is equal to mgr sin theta over bl cos theta square. We know all the numerical values here, right? We know m is 0.2 kilogram. We know that L is 1.2 meter. We know that B is 0.5 Tesla. We know the angle theta, 25 degree, and we know the resistance here is 1 ohm. So we can substitute all the numerical value here, and when you do that, you will get V equal to 2.8 meters per second. So the answer is the value of V is 2.8 meters per second.